Hello, everybody. So because we're recording, I wanted to double check. Can everyone hear me okay?
Yes.
All
Yes.
right. Fantastic.
We hear you at home.
Fantastic. Okay. So my name's Maddalena Romano. I am a doctoral student trying to finish up her PhD in a couple of months at the City University of New York in Earth and Environmental Sciences. And one of my many, many things I love to do is look at stars. And this presentation that I'm giving to you was actually a suggestion from Shannon Shaw. So I decided, sure, why not? I do Star Wars and Star Trek. Why not talk about warp drives? So we're going to talk about warp drives from their science fiction origins to their scientific possibility today. Oh, come on, click. There we are. So first things first, what is it? Well, warp drive, as it stands, doesn't actually exist. It's called an Alcubierre drive. It was the brainchild of Miguel Alcubierre, a Mexican physicist, who in 1994 suggested a solution to Einstein's field equations that could make warp drive possible. But it is still theoretical. It's a theoretical propulsion system that uh, does not propel spacecrafts through space faster than light. That's not possible because if you have mass, you would need an enormous amount of energy that doesn't exist in the universe in order to propel something with that much mass faster than light. So the idea would be to construct a bubble wherein some sort of spacecraft would sit in that bubble and the bubble itself would move through space-time. So the mass itself isn't going faster than the speed of light, the bubble is. But like I said, it's theoretical. And the issue is, like I said, it requires something to keep that bubble open as well. And that something is theorized to be negative energy or exotic matter, which pushes the bubble out so that it doesn't collapse while moving through space. Confused yet? That's all right. So am I. Let's first talk about how we would build one. Well, there's many different parts to it. And again, this is all the sci-fi parts to it. It's not necessarily how we would build one in real life. But it starts with a warp field generator, which is something that would control the distortion and create the bubble itself. And then we'd have to make certain that whatever field's being generated both expands space behind the bubble and compresses it in front so that it can move forward. And doing so would end up generating all of that energy that I told you about. And that energy is needed in order to keep the bubble stable. But the one thing that has yet to be appropriately theorized by physicists and mathematicians is how to actually navigate with that bubble. I mean, how would you guide a warp bubble system? So the physicists have sat down, they've watched scores and scores and scores of Star Trek and Babylon 5, and they've been able to figure out everything except that at the moment. So as I said, the idea of a warp drive started back in 1966 with Star Trek. And like all good science nerds, we have taken science fiction and we've made many things a reality. And other franchises have done similar things to it. Like Star Wars has hyperspace and Babylon 5 has jump gates, Dune has space folding. But it wasn't until this guy right here, can you see my hand? Can you see my little arrow here? Miguel
Yes.
Escobar. Great. He proposed the first mathematical model, and it resembles the Star Trek concept. It doesn't look like the actual Star Trek warp drive. It looks different, but his mathematical models can bring warp drive into at least a theoretical reality, if not physical reality. And his math does jive with Einstein's general theory of relativity. So how is it different? Well, when we talk about science fiction warp drives, we're usually talking about them traveling because they're using advanced engines. And that's not what we're doing in reality. Our mathematical models say that travel will be based on warping space-time. So we'd have to do something within the 4 dimensions, not the actual speed of light. And in science fiction, we have mature, reliable technology that does all of this. And no, it's just a theory. In reality, it's a theoretical concept. It is a real concept. They've been able to mathematically solve it, but there's no way to actually enact it. In fact, if anyone has seen anything on Instagram or Facebook that says NASA accidentally created the first warp bubble, no, that's not what they did. I don't know why Instagram went and said all those things, but if you search a few more of those NASA articles, you'll see that no, that's not what they did. And I'll explain what it is they did do. The energy requirements are an afterthought in sci-fi, but we have yet to solve that here. Now, there is some newer math, newer since 1994, that does reduce the amount of energy needed. So it wouldn't be the same type amount of negative energy needed, but it still doesn't reduce it anywhere near as much as we would need in order to make this a real possibility. And in sci-fi, we're used to people just traveling within a couple of minutes to different stars or galaxies and planets, and we don't have any evidence that shows that a practical warp drive can be built. So that's not even a possibility right now. But we are going to fantasize about it, and I've got lots and lots of numbers for that as well. So why do we care? Well, because without it, we can't actually travel to other planets. And that would be awful, because who wouldn't want us to expand our future? Think about becoming an interstellar civilization. Who wouldn't want to learn more about all that stuff? I mean, not to mention, just thinking about warp drive encourages so much collaboration between so many different disciplines. And it is a fun theoretical exercise, so you're really doing some sort of scientific investigation to see if it's true. Now, I'd be more interested in seeing how experimental physics could actually build it, but that's just me, because theory is great, but I'd like to see it built. Hello? Someone has a question?
Yes, I have
Sure.
a question.
What's up?
You know how if you split an atom, it'll explode, right?
Nuclear fission, yes.
Yes. Couldn't you use that same energy for that? Oh, or I have two other ones. Like there's friction that can get so hot it can start a fire if you go fast enough. And there's a and if we can do this number, if you can write a Googleplex, wouldn't that be enough power? Because that's physically impossible. There aren't enough atoms. Even if you had one atom for every single zero and the 1 1, that you still wouldn't have enough atoms to complete the entire number.
Well, as it happens, I will be talking about nuclear fusion and how that as an alternative might work. So that's a slide for later on. You're a very smart individual. That's a great question. Do you mind holding on till a little bit later in my presentation?
Yes.
Awesome. Thanks. What a great question. I like this guy. He's the next one to win an award, Ken.
Yes, indeed.
All right. So I talked about why it matters. Let's talk a little bit about some of the limitations. By the way, is anybody else just nerding out over my Star Trek console presentation? This font is called Impact, and it looks very much like the Star Trek font. I also made all of the images look like images that you'd see in Star Trek consoles for those nerds who like that type of stuff. So, speed of light, also called c, by the way, like E equals mc squared, is about 300 million meters per second, or about 186,000 miles per second. And that's the maximum speed that objects with any mass can travel through space. So what that means is that when you're approaching the speed of light, the energy that you need to move or to get faster increases. And as you're reaching the speed of light, you would require infinite energy, and that's not possible. Theoretically, not possible for an object with mass to travel at the speed of light. That's why we keep thinking about the bubble itself. Can the bubble do it? Because then the object with mass isn't traveling at the speed of light, the bubble is. So there are limitations to the idea of traveling through space-time. Now, we also have a problem of distance. So the nearest star system we have is Alpha Centauri, and that's 4.37 light years away. So at our current speed, we wouldn't get there for thousands of years because we can't travel at light speed. If you could travel at light speed, it would still take 4.37 years. And that's just not practical for us. If we had a warp drive, that could work. But we don't have a warp drive. But let's pretend we had a warp drive. What would we do if it was possible? So let me just explain this table. By the way, Alpha Centauri, for those who might not know, is right here. This is the Centaur constellation. And here's Alpha Centauri, Beta Centauri. Where's Proxima Centauri? It is somewhere in here. Anyway, at 1c, which is the speed of light, it would take 4.37 years. At 10 times the speed of light, 160 days, 100 times, 16 days. And for those that aren't figuring it out, the reason why we have all of this, 1c, 10c, 100c, 1,000, 10,000, warp 1, warp 2, warp 3, warp 4, warp 5, for those that, I just did a bunch of calculations. Weirdly, though, when you go on some of the Star Trek wikis, warp 5, 6, 7, some of these warps are weird, like the 214 times the speed of light for warp 5. Oh, okay. So I just threw those in as well so you can see the difference. But basically, at my warp 9, it could be 1.38 seconds. At their warp 9, 25 hours. But in short, we could get to Alpha Centauri in a day. Awesome.
Right.
Now, there is a sheet where I've calculated within 20 light years all the planets and stars that we could visit if we did have warp drive. And I'm going to pass that around to anybody that's interested. You're probably not going to necessarily read it, but it's cool. And I will send it around when I post my presentation to the groups.io.
Excuse me?
Hi, how are you?
I am good. Yes, it's impossible to go the speed of light.
Mhm.
Only light can go the speed of light. So, what if could we use like chemicals or something to make light a physical form of light, so we can actually travel on it?
I don't think that that is something that anyone has researched. The best that I can come up with is that light can
I'm saying
function as
like in
both
the
a particle
future.
and a wave, but I don't think there's any chemical that could make that something a bit more physical.
I'm saying in like the future, maybe. Maybe,
Not
maybe
sure I have an
because
answer to your question, but I am loving your question. So.
All right.
Okay. All right. So that's Alpha Centauri, and while some of you look at the Excel table that I painstakingly put together, let's continue our imagining. So what about Ross 128b? Ross 128b, if you remember from my last presentation, is one of many planets that mimics the Earth. It's about 1.4, I think, times the size of the Earth. And it's located right here in Beta Virginis, so in the constellation of Virgo. And we could get there at the speed of light in 11 years. If we go at the Star Trek's warp 9, we can get there in 2.65 days. And at our warp 9, the one that I calculated, in 3.4 seconds. So possible, likely. Well, we're not talking about likely. We're thinking, we're dreaming. And what about Andromeda? Andromeda is pretty awesome, right? Right now, it would take us 2.54 million years. So we're talking generation ships if we really want to get there. And even at my calculated 100 million times the speed of light, which would be my warp 9, it would still take 9.28 days to get to this other galaxy. So it's a lot. That's a lot, but a lot more possible for us to be able to get there and explore if we had some means of travel to get us there. All right, so let's talk about general relativity, because this is where it all came from. If it wasn't for general relativity, we wouldn't have warp drive. So general relativity talks about gravity. So yes, gravity is one of the four main forces, but it's less of a force than it is an explanation of the curvature of space-time that's caused by mass and energy. And objects themselves bend space-time. So space-time basically wraps itself around an object with mass. And that's what influences the motion of other objects, including light. So general relativity predicts that space-time can stretch and contract and warp along with all of this. And that also includes light, does the same thing. So warp drive would basically propose that a spacecraft could travel by doing the exact same thing rather than moving through faster than light. So if some of you have been thinking about this, is like, well, how are they doing that? They're expanding space in one direction, contracting it in another. If we're thinking Einstein-Rosen bridge, otherwise called wormholes, you'd be right. They're making mini wormholes and contracting it in front of them, expanding it behind them, and the bubble closes as they move. That's how it would work. So these objects would then move along these curves instead of being pulled by gravity. I found these awesome little animations, and I thought you'd like it. So this first one that you see is 4D space. So space-time is four-dimensional. So we know our dimensions, their length, width, and height. Those are 3 dimensions. Time would be the 4th dimension. So it's a 4-dimensional fabric that combines the 3 dimensions of space, which is part of the Euclidean geometry, like I said, X, Y, and Z, with time. And time can be, I usually use M for time, into one single continuum. And this is called a tesseract. Yes, you Marvel fans, tesseracts do exist. They just don't glow blue, but they do exist. This is what you're seeing in the very first one. So then we have something called the Clifford torus, which is also called a hypersphere. That's this one down here, that second animation. And this is a set of points in the same 4D space that has the same distance from any fixed point. Why do we care about this? Because as part of the Friedman, I'm going to say this wrong, Lemaitre and Robertson-Walker metric, R is substituted by the function RT, with T meaning time, right? So it's the cosmological age of the universe. What that means is that R is going to grow and shrink with time, meaning it expands or collapses with the universe, depending on the mass or density. So if it wasn't for this little hypersphere, we couldn't start thinking in terms of, oh, it might be possible to travel through space because it will expand and collapse And that is what we needed in order to start thinking of this warp bubble. So now we have some of the math behind it. How do we bend space? If space-time can be bent, then it might be possible to use those distortions for travel. So as you see here in this image, you have some sort of spacecraft, whatever type of vessel it is. The outside has a bubble, and within it, there's negative energy. So negative energy in the front of any vessel is pushing outward, and it's doing the opposite behind it. So it is compressing in the front and expanding in the back. If you're not sure, just have a look right here. Compressing, because you have arrows pushing in the front, and you have all these arrows pushing out from here and out from here, much larger in the back. There are many visualizations we can look at where you will see this a bit more clearly. I'm sure you might have if you're already interested in stuff like this. So what that means is that the spacecraft can move through time because it's going to be pulled forward because of this compression and expanded behind it. So craft remains within the bubble and the bubble itself moves. This is called the Alcubierre drive. So warp drive does not exist in our time, but Alcubierre drive does. So it's this solution to Einstein's field equation suggests that we can get to faster than light travel. We would just need something called negative energy or exotic matter in order to get this to work. And you would need enormous amounts of it, which does not exist and which we don't know how to get that to work. So, but this is what I see this top image. Here's our little spacecraft. It's kind of cute. Here's the expansion behind us and the contraction in front. And so the craft would move in this direction. Here's a much better image. And this, technically speaking, is an imagined spacecraft that would use the Alcubierre drive. So this is what they're talking about when you think of warp drive. It's not the USS Enterprise, although they are working on one that could be also named Enterprise, IXS Enterprise, so we shall see. So let's talk about this exotic matter that I keep mentioning. It's tiny negative energy. And we have observed these effects in quantum phenomena. It's something called the Casimir effect. That's what these scientists were able to do that got all of these reporters that know nothing about science so unbelievably excited. And they said, oh, look, we created a warp bubble. No, we didn't. What we did was observe the Casimir effect. So see right here in this bottom image, you see the compression, you see this little push in between. That's the Casimir effect. So in microscopic amounts, there was a bit of negative energy being created and it pushed out. But we don't have any technology right now that can produce sufficient amounts of it in order for a warp drive to be more than theoretically possible. So this is the true what we've been able to do, not what was on Facebook and Instagram. So if we can't do this because of negative energy, then what can we do? Well, there's something called a subluminal warp drive, not subliminal. I made that mistake too. Subluminal warp drive. So early models required too much energy. We've been talking about that, and it doesn't exist in the observable universe. So what if we traveled just below the speed of light, hence subluminal warp drive? It does distort space-time, but it travels below the speed of light. And the second image down here, that's a better image of what the drive would look like. Technically, it's what the craft would look like, and those rings around it would just be creating some gravity.
Can I ask a question?
Yes. Sure. What's up, Ed?
Is there any correlation between this negative energy and what we are theorizing is dark energy?
No.
Okay.
That was one of the many things that I looked up because I anticipated that question. They're not the same thing because dark matter or dark energy, it functions along the same as regular mass. Antimatter functions the same as regular mass. So this would have to be negative energy. It's not the same.
All
It's
right.
a
Thank you.
fantastic question. I knew someone would ask that. Thanks, Ed.
They paid me to ask you that.
No, I did expect when I heard negative energy and exotic matter, oh, someone's going to ask me about this. So I made sure to look that up. They're not the same. But basically, because you're traveling below the speed of light, you're not violating Einstein's speed limit. And that way you don't have to worry about causality. We're going to talk about causality. And if anybody wants to bring up time dilation, I am going to talk about time dilation. If you don't know what that is, that's okay. We're going to talk about it. So there's still some major engineering issues if you want to travel below the speed of light, but it could be a possible alternative. All right, so let's have a look. So let's say we wanted to travel to Alpha Centauri. And if we went at below the speed of light, I mean, it could take us at 1% of the speed of light, it would take us 437 years. But even at 99% the speed of light, again, not even light speed, it would take us 4.41 years. So we'd still be living on a ship for 4.41 years to get to Alpha Centauri. So and at light speed, it would take 4.37. So, there's still issues, especially if we want to travel much further than Alpha Centauri. So let's talk about the warp bubble itself. In order for a warp bubble to work, it has to remain open. If it starts to contract to Earth, well, so much for us. So any type of disturbance could cause it to collapse or become uncontrollable. And then that's it for us being able to travel to wherever we need to go. And possibly that's it for the actual craft itself. So we have no idea how to create the bubble and keep it stable right now. This is the part of theoretical physics has not been able to solve. And it's one of the largest unrealized challenges. I'm sure someone will figure this out within the next 100 years, but we won't be here to experience it, unfortunately. Now let's talk about causality. So faster than light travel could create something called the causality paradox. That's where cause and effect no longer occur in expected order. We've all seen this in all of our sci-fi, how someone goes back in time and causes the very thing that created them in the first place, or like how they were their own ancestor or whatever it was that they needed to do. It happens all the time. People love it in sci-fi, but it's a paradox. How on earth could it possibly happen, and when could it have possibly started? Now, some models suggest that any type of closed time curve could do something like that, could resemble something like time travel. Not the time travel we're thinking about, we would go back to the past, but basically the idea would be that whomever, well, you know what, we're going to talk about this in the next slide, so I'm not going to go mixing the things up. But basically, your present and your future self would be existing at different times. So you have an observer on Earth and you have yourself, and the idea is that one second. The person who's on Earth is observing time going slower than the person in the craft itself. And that can lead to, oh, well, this happened before that happened. I don't have an answer for that or for why exactly that would happen, but there is an overlap, like a Venn diagram overlap with this particular oh, why am I just forgetting this particular concept called time dilation? So we've proven that time dilation does exist. Mathematical experiments have proven that it does exist. We've confirmed it with atomic clocks, with GPS, high-speed particles. This does exist. So it just means that when an object travels closer and closer to the speed of light, time passes more slowly for the traveler than for somebody at rest. So what that means is that the faster you're traveling, the slower time is for you than it is for other people for whom time is traveling at the regular speed. It's where you see like two twins leaving at the exact same time. By the time the twin comes back, they're one has aged barely at all, the other one is a much older person. That's the idea. So for interstellar travel, astronauts could experience less time than people that are remaining on Earth. And that's something that has yet to be addressed or solved. I wouldn't know the first way to address it or solve that myself. Oh, come on, let's go. All right, so where's the current research? We're still studying it. And we're still trying to make the math work for all concepts and keeping within the general theory of relativity. And they are exploring ways to reduce the enormous amount of energy requirements. Again, subliminal warp drives are one way. And there are advances in quantum physics and what have you that might provide some new insights, but it's still an area of active research. We don't have a physical solution, but we do have a lot of research ongoing. We have some alternatives, and one of them is nuclear fusion propulsion. So instead of using warp bubbles, we could use fusion reactions from split atoms for high efficiency, long duration thrust. We can use antimatter propulsion again. Same thing, split the atom. Well, no, I'm sorry. Nuclear fusion is my mistake. Nuclear fusion is different from antimatter propulsion. Antimatter, you split. Nuclear fusion, you fuse. My mistake. So that could provide a lot of high energy density for extended periods of time. We have laser sail propulsion. And that could, I believe, did we use laser sail propulsion for the James Webb? Why do I want to say yes? No, I don't think that we did. I don't think we did. And it uses powerful lasers to accelerate a spacecraft that uses this sail. And then the sail goes from there. And then there's always, and we've seen this many times on many different sci-fi, generational ships and cryogenic sleep, where individuals are put into a hibernation state in some sort of generational ship that then takes them to another planet. So what have we learned? We're almost done, people. Warp drive's theoretically possible, but it's completely unproven as of right now. It does work by warping space-time, but there's a lot of challenges to it, challenges we still have yet to get over. But the research continues. And if it can be realized, then wow, we could actually be exploring space. And that's the thing that I think we really need to think about. I mean, science fiction inspired physicists who have been able to prove that this is theoretically possible. And that could mean that we might have a propulsion system that could have us exploring other solar systems, other galaxies, and sometimes. So thanks everyone for giving me your time. If you have more questions, I'd be happy to answer them. If not, there are still coffee and donuts.